Now we are going to learn about dependent events. In a previous video, we learned about independent events. And to introduce the independent events, we drew starbursts out of a bag. Now, to talk about dependent events, we're going to do a different game. In this game, we have 5 cards in our hand, and those cards will be ace, ace, so 2 aces, and then we'll have the 3 kings. That's all. We're not dealing with a full deck of cards. The way this game is going to be played is one player will hold the 5 cards, or you could set them down on the table, and then the other person will draw a card, or if they're on the table, someone will just draw a card. And we'll look at that card, we'll document what that card is, and then we'll set that card aside. So now there's only 4 cards left in the sample space. And that's what it means when we're talking about without replacement. Okay, so we draw a card, we look at it, we take it out of the deck, and then we draw another card. If the cards match, meaning if we get 2 aces or 2 kings, then you win. So for example, I did this for a couple rounds in my face-to-face class, and the first card was an ace, the second card was a king, so that was not a winning hand. Then I did it again, and I had a king, and then the king was removed from the deck, and then next I drew an ace. So again, I was not a winner. Then I got all 5 cards back on the table. The first card I drew was a king. The king was removed from the deck. The sample space changed. And then I drew another card, and I happened to get a king this time. So I was, in fact, a winner. Then I had every table do this same game to figure out what is the probability of winning. So one group got 4 wins out of 10 games. So their probability of winning was 0.40. Then we recorded every group's number of wins. So one group had 4, another group had 6, another group had 4, and another group had 3. We only had 4 groups there that day. So that was a total of 17 wins. And each of those groups played 10 games. So that was 40 games that have been played. Well, this will equal 0.425 or 42.5% probability of winning. Now, what makes this example interesting and different than the starburst example is that the card was actually removed from the deck. We did not put it back in. So when we remove the card from the deck, the sample space changes. So we can't find the probability by just multiplying the probability of event A and the probability of event B. We need to do something more. So to illustrate how we're going to approach this probability, we're going to start first with a tree diagram. All right, first let's define a couple things. We're going to say event A is the first card is an ace, and event B is the second card is an ace, because we want to win. All right, so let's look at this. So here's our deck of cards. The probability that the first card is an ace is going to be 2 out of 5. And that's how we put it in the tree diagram. Then the probability that the first card is a king, as we can see, we have 3 out of 5. All right, now we're going to work each branch. So think about this. The first card is an ace. So that means that card has now been removed from the deck. So what is the probability that the second card is an ace? Well, there's only one card that's an ace out of 4. The sample space has changed. It's not 5 cards, it's 4 cards now. And then the second part says, so if it's 1/4 that the second card is an ace, there is 3 cards out of those 4 that are not aces or are kings. So to find the probability that the first card is an ace and the second card is an ace, I'm going to multiply 2/5 times 1/4. And I'm just going to multiply straight across so I get 2/20, and that'll be equal to 1/10. In a similar manner, I can multiply to find the probability that the first card is an ace and the second card is a king. I'm going to do 2/5 times 3/4. So this will be 2/5, that's the probability that the first card is an ace, times 3/4. That is the probability that the second card is a king. And when I multiply this together, I get 6/20, and then that'll simplify to 3/10. All right, let's try the bottom branch of this problem. All right, we already have the first box filled out. The probability that the first card is a king, well, there's 3 kings out of 5 cards, so that's going to be 3/5. So imagine this deck. We have a king, and we are going to now remove it from the deck. So the sample space has now changed. That's what makes this a dependent event. We're changing how many possibilities there are. So I'm going to go here to the second card as an ace. I'm going to look at right here. I have 2 aces out of a total of 4 cards. So the probability that the second card is an ace is going to be 2/4. The probability that the second card is a king, well, I do have 2 out of 4 kings. So that's going to be 2/4. Now I want to find the probability that the first card is a king and the second card is an ace. I'm going to do exactly what I did before. Here's the probability that the first card is a king and the second card is an ace. So I'm just going to multiply those together. 3/5 times 2/4. This is going to be 6/20, and that'll simplify to be 3/10. Now I want to find the probability that the first card is a king and the second card is a king. So that's going to be 3/5 times 2/4. And this will be the same 6/20. The important thing to notice is that the probability of the second event changes based on whatever happened in the first event. So if an ace was drawn or if a king was drawn, that changes the probability for the second card. The last question says, are the 2 cards drawn one right after another without replacement independent or not? We already covered that. They are dependent because the sample space changes. Okay, we're going to go ahead and define some things and a formula, and then we'll go back and add some notation to our tree diagram. All right, first is the definition for dependent events. And this is for 2 events, A and B. The outcome of one event affects the outcome of a second event. Now, the general multiplication rule for dependent events is going to be the probability of A and B, or A intersection B, is going to be the probability of A, which we're pretty familiar with. But the thing that's different is we're going to multiply the probability of B given A. This vertical line is given. It's not a division sign. It is just a up and down line. Okay, so let's go ahead and go back to our tree diagram and fill in what these little pieces mean. All right, let's just take this top row. This is what we are finding. The probability of A and B. That is what we're solving for. Now let's go back to the beginning. We had the probability that the first card is an ace. This is our probability of event A. Then this is where it gets real interesting. Now we only have 4 cards left. And of those 4 cards, only one of them is an ace. That's what this is. That is, there's 1 out of 4 cards that could be an ace. Another way to write this is probability of B given A. The probability of drawing an ace given that the first card is an ace and we took it out of the deck. So what we'll do is we're going to multiply the probability of an A times the probability of B given A, and that's going to be this probability of A and B. That is our multiplication rule for dependent events. The last thing I want to do is illustrate the tree diagram and where all the probabilities are. So this is A, and I'm going to call this A complement. And that's a notation we learned at the beginning of the unit. So this will be probability of A, and this will be probability of A complement. Just to keep the notation organized, I'm going to call this event B or C. So this will be the probability of B given A, and this will be the probability of C given A. The event of B given A means this is the probability that event B is happening given that something already happened with A. And then if I multiply these two together, then I get the probability of A intersection B, both things occurring. Then if I multiply the probability of A times the probability of C given A, that will equal the probability of A and C. I can also have events B and C occur if A complement occurs. So here's B and C. So this is the probability of B given A complement, and this is the probability of C given A complement. So in our previous example, drawing the king, that was our complement rule. And if I multiply those together, I'm going to get probability of A complement intersection B here. And then if I multiply A complement and C given A complement, I'm going to get probability of A complement intersection C. So now that we kind of have a foundation of what dependent events look like, go ahead and try problem 5 and problem 6 and see if you can't find those dependent event probabilities.